In this problem, we're looking at an L-shaped bar, which is pinned to ground at B. There's a roller support there at C, and there's a vertical force in D, with this vertical force being P. What we're asked to do here is determine the vertical deflection of point D on the structure. And what it doesn't say here, but I'm going to decide to do here, is to ignore the effects of shear. We're going to use Castigliano's approach, but whatever approach we use, we first need to find our external reactions. So I'll use equilibrium in order to determine the reactions there at B and C. To do so, we will draw a free body diagram of the whole thing. The loads that we have acting on there is the applied force P. We have the roller support there at C, and then we have the pin joint there at B. So this is BX and BY. Our goal here is to find those reactions. What I'm going to do is do a summation of moments about B. Summation of moments about B gives me CX times L1, and then I have a minus the load P times the length there of L2. So what I have here is that CX here is equal to L2 divided by L1P, and for the dimensions that we have provided, that's 4/3 P. So the next thing we need to do is find our internal resultants. Since we're not going to be including shear effects, effectively what we're doing is finding the internal bending moments there of M. I'm going to break the structure mathematically into two parts. This is going to be one, the vertical piece, and two, the horizontal piece. So in the end, whenever I write down my strain energy, I'll write it down for one and write it down for two, and then add them together. So for one, what I need to do is make a cut, a mathematical cut, through the member somewhere in section 1. What I'm going to do is, again, make the cut in section 1, and what I'm going to do is I'm going to keep the lower right part. And the reason for this is I didn't bother to find CX and CY. So by doing it this way, I can avoid finding those. I'm going to have a shear force there of V1, a bending moment of M1. I'm going to have an axial load there of F1, and of course my reaction there at C, which I found through equilibrium. So first thing I will do is sum forces in Y, and I'm going to use Y positive up, X positive to the right. So there what I get is F1 minus P. So with that being equal to 0, it says that the axial force F1 as a function of, and I'm going to call the variable along 1 to be Y. So F1 of Y is a constant there of P. If I do a summation of moments about, let's say, this point where I made the cut, let's call that K, what I have is minus M1. I have CX times the moment arm of Y. I've got P times the moment arm of L2. It's going to be in the minus Z. That's 1, 2, 3. For equilibrium, that's a 0. So M1 as a function of Y is going to be equal to 4/3 Y minus the length there of L2 times the applied load there of P. So that's what I have for section 1. For section 2, I'll do the same thing. I'll make a cut. Through section 2. I'm going to take the same approach that I did before. When I make the cut through 2, I'm going to keep the lower right hand side. That way I don't have to worry about the reactions there at B, which I didn't find. So this is P, and the forces, the shear force, V2. I'm going to have the bending moment, which I'll draw this way for M2. This is going to be at point H. And that's it. And in addition to that, I'm going to call the location of that X. X being measured from the right. So when I sum my moments about H, what I have is minus M2, and I have a minus P times X. So therefore, equilibrium gives us that the bending moment M2 is equal to minus PX. So this is what I'm going to use for section 2. This is what I will use for section 1 for bending, and this is what I'll use the axial force for member 1. So I've got all of the pieces that I need. So whenever I write down my energy expression, U is going to be made up of what comes from 1, add on to what comes from 2. So from section 1, I'm going to have the 1 over 2 EI integral from 0 to L1 of M1 squared dy. I'm going to have a 1 over 2 EA integral 0 to L1 of F1 squared dy. And then for 2, I'm going to have 1 over 2 EI 0 to L2 of M2 squared dx, like this. So again, this is for section 2. This is for section 1. What I want to do is find the vertical component of displacement there at D. What that's going to be is using Castigliano, I'm going to do a partial of my expression U with respect to P. I do the differentiation, and I get 1 over EI, 0 L1, M1, partial M1 with respect to P, dy, plus 1 over EA, integral 0 to L1, F1, partial F1 with respect to P, dy, plus 1 over EI, integral 0 L2, M2 partial M2 with respect to P dx. So what I have here, whenever I put in M1, I look back at my expression for M1, and that's 4/3. Y minus L2 going to be a squared dy. And there will be a factor of p, which I brought out there on the outside. I have a 1 over EA, integral 0 L1. F1 we saw was equal to P. Partial F with respect to P is just a 1. And the last term there is 1 over EI, integral 0 to L2. M2 was given by minus PX. Partial of M2 with respect to P is going to be a minus 1. I'm sorry, minus X dx. So this is going to be a positive px squared. This p can come on the outside. And by the time I do my expansion of the first term, by doing the square, doing my integration, what I end up with is p over EI, 16 over 27, L1 cubed, minus 4/3, L2 L1 squared, plus L2 squared L1, plus P L1 divided by EA, plus P over 3 EI L2 cubed. So this is going to be the deflection y direction there at D.